Now we're going to move on to more general contingency tables. The tables do not need to be 2 by 2. We can actually have R by K contingency tables, where R is the number of rows and K is the number of columns. So again, we're going to look at this data about liver disease and drinking, but now I've split it up, drinking, into heavy drinking, moderate drinking, and non-drinking. Okay, and this is actually the data that I presented to you back in Math 350. Okay, and this is an example of what's called an R by K contingency table. So this is a table that has these tables have a couple different contexts that we can have. We can look at one variable with R categories observed in K independent samples. Okay, so we could look at something like college graduation rates. So we could look at the total number of people who graduate or don't graduate. Okay, but then we can do that over K different years. Or we could look at it over K different demographic groups. You could also have two variables, one with R categories and one with K categories. So for example, you could have a group of people with and without liver disease, categorized by several drinking levels. So the null hypothesis is going to be the same. We want to say, for example, that the probability of liver disease, given you're a heavy drinker, is equal to the probability of liver disease given you're a moderate drinker, is equal to the probability of liver disease given that you're a non-drinker. Essentially, okay, liver disease and drinking categories are independent. Okay? But this is a compound hypothesis, kind of like when we were doing ANOVA. Okay, so the alternative is that at least one probability is not equal to the others. So you have dependence for at least one category. So again, we're going to have these hypotheses where, yes, we're going to be able to say whether statistically liver disease is dependent on drinking category, okay, but we're not going to be able to say which one based on this kind of test. Now, for an R by K contingency table, we're going to have to compute expected frequencies. So that's going to be the row I total times the column J total. And then we're going to divide by the grand total. So that's not going to change. But the degrees of freedom in this case is going to be R minus 1 times K minus 1. So before, you'll notice that we had 2 minus 1 times 2 minus 1 gave us the degrees of freedom of 1. Okay, now when we have more columns and rows, okay, so as long as we specify R minus 1 rows and K minus 1 columns, then we've specified the entire table. The chi-squared statistic in this case will then be a sum from I equals 1 to R, and then another sum from J equals 1 to K for the number of columns. okay, OIJ minus EIJ squared over EIJ. Okay. So now we want to move on back to our example and conduct this test. Okay, so we want to find the chi-squared statistic and the associated p-value for the liver data above, and then ask ourselves, what can we conclude? Okay, I'm going to add right here that alpha is going to be 0.05. Okay, and in order to do this, we're going to have to compute the expected frequencies. So for example, I'm going to take my I'm going to take my 121 times 70 divided by 1,000, and I'm going to get 8.47. Now, you should notice that as soon as I get that 8.47, that's going to determine that the other expected frequency is 112.53. They need to add to 121. So the second one was dependent on the first. In fact, I'll write it as this one. I'll write it as 112.53 in red because it was dependent on the blue one. For moderate drinkers, the expected frequency is 686 times 70 over 1,000. That's 48.02. Okay, but now that I've determined that, okay, then the other one, I have to add up 637.98 if I want that to add to 686. Now going across the row for the non-drinkers, if I add up 8.47 and 48.02, I need to add 13.51 in order to get 70. And then if I add the 112.53 and the 637.98, I'm going to need to add 179.49 to get to 930. So that you can see that I only needed to specify two of them, the two blue expected frequencies, in order to get the rest of them. Okay, that tells me that the degrees of freedom in this case is going to be r minus 1 times k minus 1, okay? So that's going to be 2 minus 1 rows by 3 minus 1 columns, which gives me 2. Now the chi-squared statistic, in this case, is going to be, okay, we're going to take observed minus expected squared over expected, and then we're going to do that over and over again. Observed minus expected squared over expected. Here we've got 7 minus 13.51 squared over 179.49. We have another one, which is 93 minus 112.53 squared over 112.53. Hopefully you're noticing how tedious this is becoming, so that you're thinking maybe you would want to put this into some software. You can check your R reference sheet, and that tells you how to put in the data into R so that you can run this test, and you don't have to do this by hand. But observed minus expected squared over expected. And look, see, I've even made a mistake. That's supposed to be 13.51. Okay, so we add up all of those, and we're going to get 55.59. Okay, that's a very large chi-squared statistic. Okay, we want to know, again, what is our rejection region in this case? Okay, so we want chi-squared to be greater than the 5%. Okay, so we're going to go to our chi-square, and now we're going to do the degrees of freedom 2. Okay, and so we need it to be bigger than 5.99, which it certainly is. In fact, it's way off on the chart here. Okay, and so we know that the p-value is less than 0.005. Okay, so chi-squared needs to be bigger than, going back and looking, 5.99, okay? In fact, the p-value in this case is less than 0.005. If you do use some software, it will say that the p-value is 8.49 times 10 to the minus 13. Okay, so what that means is we can reject the null hypothesis. Okay, so we can say that liver disease depends on drinking status. But we cannot conclude which status has a different probability. Okay, so not as strong a conclusion as we would like. Okay, we can see that it does depend on drinking status, but we cannot conclude which status has a different probability. Okay, so recall that the expected frequency of each observation should be at least 5. Okay, and if it's not at least 5, you need to join together some of the categories with small frequencies. Okay. I want to point out that in the last video, we actually did with the hair and eye color have some frequencies that were less than 5. And so you would need some, you can't join together categories with the 2x2 contingency tables. So you would just need more data than what I was able to collect from you guys. Okay. Because we have a compound null hypothesis with multiple parts, we cannot tell which conditional probabilities are not equal when we reject the null hypothesis. Okay, so we couldn't tell which ones were not equal, but you can follow up with a post hoc test. And those involve simultaneous or pairwise comparisons. Okay, so you can use something like the Bonferroni method. Okay, you just need to have a component-wise error that's smaller, okay, than our experiment-wise error. So you can run these with 2x2 contingency tables if you want. I highly recommend that you do. If you do that, you would see that heavy drinking is different statistically from moderate and non-drinking. Okay, so moderate none, you aren't able to tell if there's a difference between those two. Okay, so we can't reject the null between moderate none, but we can reject the null between heavy and moderate and heavy and none. So it appears that heavy drinking is what has a dependent relationship with liver disease. Okay. I also said that for the homework that it would be on a worksheet. Turns out I found a good problem in the book, page 726, number 16. So that is your homework problem for this lesson.